Welcome, everyone. Welcome. Aloha, biostatisticians. And why do I say that? Because you are already biostatisticians. You're doing it. You're doing biostatistics. You're doing it. So you're already part of the gang. Okay. It's just a matter of taking more steps as you progress. And today we're going to take a really important step, a super important step. So I want you to pay close attention. All right. And I know you probably won't remember everything, and that's okay. Nobody can. That's why I said you got to read the book. So let's see. Read the book. Really, read the book. 2 chapters this week. Again, 2 chapters. We're not going to have a lot more reading after this. There is maybe 1 more chapter I think I'm going to assign, but get this stuff down well. This is foundational. Chapter 3 and chapter 4. Chapter 3 is on scatter plots and correlation, and chapter 4 is on simple linear regression. The book is really helpful. It's going to tell you a lot. You can get this from a lot of other sources. There's a ton of other places where you can find this information too. For example, ChatGPT, the internet. Here's another video. I'm going to send this to you in the next email about regression. And there's another one that I sent you already about correlation and causation. Whoops. You don't need to see that. That's the ad. Lots of good sources, but go ahead and use them. And we will definitely have a lab on Thursday where we'll examine our own data as usual. But for now, I have a long lecture for you. A long lecture, so strap in. All right. Exploring relationships. It's all about like a relationship. Like, how do we feel about our relationship? We started exploring relationships last week when we talked about the chi-square, but now we're going to go further into it and introduce a couple of tools, 2 tools, correlation and regression. Correlation is a really basic tool, and regression sort of builds on it to become a more flexible tool. We're going to start with a simpler form of it and then go from there in the coming weeks. Again, you are assigned, it is required to read chapters 3 and 4. We will have a quiz, and the questions will probably be taken from the questions that you see at the end of these chapters. That's my plan. I haven't made the quiz yet. I'm still working on it. I just want to make sure it's really relevant. So read chapters 3 and 4. It won't take that long. 2 hours, something like that. Remember, for every hour you spend in class, you should spend at least 2 hours doing something else related to the class. So that's a big assignment. And you won't have another homework this week because we're going to have a midterm next week. All right, so we got a quiz this week on Thursday. Next week on Thursday, midterm. Tuesday next week, we will review for the midterm. Do we have questions?
Yeah, will the midterm be online?
Yes, midterm will be online.
This
Be
is
an online.
Are these chapters from the book?
Yes, the Baldy and Moore. Yeah. Baldy and Moore chapters 3 and 4. Fun reading. Fun reading. You know, or if you have insomnia, maybe it'll help. Here's the outline of the lecture. First, we will go over questions that can be answered using correlation and regression analyses. We'll talk about the hypotheses for both of these tests, the conditions under which the tests are valid, the calculations, the maths, the graphs, the interpretations, and some of the dangers. Yeah, danger lies ahead. Questions. Questions for these tests are pretty similar, but note there are subtle differences. There are subtle differences. All right, with correlation, you could ask, for example, how does drinking beer affect blood alcohol level? And if you do a regression, you could ask more specifically, how much does blood alcohol level change per beer drunk? With correlation, you could ask, how does children's height change with age? With regression, you could ask, what is the predicted height of a child of X age, whatever age you put in there? 5 years old, 8 years old, 10 years old. With correlation, you can ask, how are changes in coral reefs correlated with water temperature? With regression, you can ask, how much can change in coral reefs be explained by changes in water temperature? With correlation, you can ask, what influence does the number of registered powerboats have on manatee deaths? And with regression, you could ask, how many manatee deaths can be predicted by X number of registered powerboats? And how much does year-to-year variation in powerboat registration explain the number of manatee deaths? So right away, you can start to see that correlation gives you a really neat way of asking questions, but with regression, you can get a lot more information. Hypotheses. The hypotheses are fairly similar, subtle differences. Again, with correlation, the null hypothesis is that there is no linear correlation between variable 1 and variable 2. And this could be stated as rho. Rho is equal to 0. Rho is the Greek symbol for the population correlation coefficient. Remember, we never really know anything about the population, or very rarely do we know anything about the population because we never have the whole population. We have a sample of the population, right? So we're testing the hypothesis within bounds of our confidence intervals. Does rho equal 0? The alternative hypothesis is that there is a linear correlation between variable 1 and variable 2, or rho is not equal to 0, or you could state it as rho is greater than 0 or rho is less than 0, depending on whether or not this is a two-tailed, not equal to 0, or a one-tailed hypothesis, greater than or less than. For regression, the null hypothesis is that there is no linear relationship between X and Y. It's kind of the same, but it's a little bit different. For correlation, variable 1 and variable 2 can be on either axis. They're interchangeable. You can put your X on the horizontal axis, or variable 1 could be your X, variable 2 could be your Y, or you could switch them and it's equally valid. And that's because you don't really expect that Y is caused by X. And we'll go into some examples of that. For regression, there is no linear relationship between X and Y, and X matters. Which one you put on X matters because you think that X probably has an effect on Y. And if we look at some of the questions we were looking at, how does drinking beer affect blood alcohol level? Well, there's an obvious X, right? Drinking beer probably affects blood alcohol level. But does blood alcohol level affect drinking beer? Probably not. Probably not. How does children's height change with age? Well, you almost could switch those axes, right? But for the other ones, no. Obviously, the changes in coral reefs don't affect water temperature, but water temperature probably affects changes in coral reefs. So depending on the data, depending on the question, you might think that a correlation would make more sense. I think the example that makes the most sense to me is when you're looking at allometry with the null hypothesis. Allometry, I'm not talking about the tree called llama. I remember when I was telling my friend about a paper I was writing on allometry, she's like, wow, must be one really cool allometry that you're writing about. I'm like, no, allometry, ALLOMETRY, is the study of how the size of one thing relates to the size of another, more or less. And so you could say, what is the relationship between, say, the length of my hand and the length of my entire arm? Now, which one is X, which one is Y? It's not really obvious. You could put either one on the X axis or the Y axis. One isn't really predicting the other one or causing the other one, but they're related to each other. It just could be that either one is X or Y. Okay, so for regression, the alternative hypothesis is that there is a linear relationship between X and Y. And here we would say it mathematically as either beta which is the slope coefficient, is equal to 0, or beta is not equal to 0, or we could test it with a one-tailed test of beta is greater than 0 or beta is less than 0. That's the slope coefficient. Subtle differences. Conditions. The conditions are slightly different too. You can see that correlation has fewer conditions. It's a little easier in a sense, but you get less out of it. So it's worth it to try to do the regression. But with correlation, you're asking if two numeric continuous variables are related in a linear way, right? So they have to be numeric continuous variables, two of them. Remember, with chi-squared, we were testing relationships between two categorical variables, right? Now we're looking at two continuous variables. With the t-test and the ANOVA, it was one categorical, one numeric, right? Then t-test was two categorical. Now we've got two numeric. See the pattern? All right, again, correlation, it has to be a linear relationship. Number 3 condition, independent observations and normal distribution for both variables. You check to see that both variables are normally distributed or can be transformed to be normally distributed. And we'll talk more about that a little bit later and also in the lab. And again, a big difference here is that with correlation, X and Y can be switched. With regression, the conditions are a little bit harder to meet. You need to have two variables or more. We're going to start by talking about simple linear regression, which has just two variables, but regression is the multi-tool of the statistics tool set. You can have lots more variables, usually just one Y, and usually that Y is numeric. But the explanatory variables, the X variables, can be numeric or categorical or mixed up, which is great. We're going to start with the two numeric variable case. That's the simplest form, but we'll soon go on to adding categorical variables. We also have to assume a linear relationship between X and Y variables. Again, this is simple linear regression. Is there such a thing as non-linear regression? Absolutely there is, but we won't cover it until the very end of the semester. Again, we have to make sure that all the observations are independent. Otherwise, we have to do a different kind of analysis. And here we're asking if the distributions of Y at each level of X are normal, right? And so if you look at this graphic up here, you see that for every Y, you want to have normally distributed, for every X, for each level of X, there has to be a normal distribution of Y. Is that really easy to figure out? It's not that easy exactly to figure out, but there are ways to test this, and we'll get more into that. You also want to check that the variances are equal. We talked about this before, remember, with the t-test and with the ANOVA, and we said with t-test, don't assume equal variances, use the Welch's test instead, so much simpler. And with the ANOVA, we said, yeah, you do have to assume equal variances, and you check that. Remember, it was, what was it? The standard deviation of the largest standard deviation has to be less than 2 times the smallest standard deviation for ANOVA. That's how we check for equal variances. In this case, we're going to check for equal variances in a different way, but you still have to make sure that they're equal. And by equal, in this case, we mean that they're constant and normally distributed. That means that the variances around each X for the Ys are normally distributed, and also that the variances don't change along the Y axis. You don't have lower variation at lower levels of X and higher variation in Ys among higher levels of X. And again, we'll get to testing that. It's a little bit of an art, but we'll start to get into it mostly in the lab. Again, big difference between correlation and regression is that X is expected to affect Y, but not the other way around. You have to think about what makes sense to put on your X axis versus your Y axis. Calculations, the maths. Let's take a look at this equation. Equation for correlation. R, the correlation coefficient, also known as Pearson's R. And if you want to look up who Pearson's was and send me a message, I'll send it to everybody because I don't know. Some guy who figured out something. I'm sure he was great. Anyway, here's the equation. We start off by saying we're going to multiply the sum of all this by 1 over n minus 1, which we've seen before, right? Basically, we're putting n minus 1 on the bottom of the equation. We're going to divide by n minus 1, which is our degrees of freedom. Seen that before. The number of samples minus 1. And this whole big sum thing, I know it's like, whoa, what's all that? It's not that hard, actually, if you break it down. Just let's take one piece of it. Let's take one piece of it. Let's take what's in the parentheses here. Xi minus X bar. Xi is just that individual X variable minus the mean of that X variable. Hey, we've seen that before too. We've been seeing that since the t-test, right? We even calculated it for our standard deviation, right? Yeah, it's basically how far away is that individual observation from the mean of all the observations for that variable. How much variation, how much distance is there on a number line? And you divide that or standardize it by dividing by the standard error of that variable. It's pretty simple. All you need here is the same thing we had before. You need an n, you need your means, and you need your standard deviation. And then you do that same thing for your y variable. You take the individual y variable and subtract the mean of all the observations of the y variable and divide that by the standard deviation of y, right? And you do that for each one. And okay, that would take a while. All right, yes, this would be extremely tedious to try to do by hand. We are not going to do it all by hand. I'm not sadistic. We're going to let computers do it for us, but just recognize that what goes into this is not so different than what we've seen before. It's just building. It's building blocks, right? So with the correlation, what we get here again is R, which is the correlation coefficient, otherwise known as Pearson's R. And what this tells us, this is what I want you to really know. Pay attention, going to be on the test. What you got to know is that the correlation coefficient measures the strength and the direction of the relationship, okay? And its values range from either -1 to 1. -1 is a perfect negative relationship. 1 is a perfect positive relationship between your X and Y, or between the two variables, right? Got it? Simple stuff. Next, we think about regression. In regression, we have something called the R squared. What is R squared? It's as simple as taking this correlation coefficient and squaring it. R squared is R squared. Simple, right? Well, okay, that's true for simple linear regression. When it comes to multiple linear regression, it's a little more complicated than that, but it's essentially the idea. And for simple linear regression, which is what we're going to do this week, it totally works. The R square is called the coefficient of determination. And what it actually gives us, which I think is so cool, is the fraction of the variation in Y that's explained by X. Like, how much does X affect Y? How much does it matter? How much does temperature, how much, like what percentage of the variation in temperature changes the coral reef? What percentage of the variation in registered powerboats, what percentage of the variation in manatee deaths can be explained by the number of registered powerboats? Like, how important is this variable, right? Does it make a big difference, small difference, right? Is an R squared of about 0.1, like 10%, or like 0.5, like half, or maybe even 0.89, like 89% of the variation is explained? That's pretty high. You'd want to know about that, right? And the values range from 0 to 1. Of course, you can't have negative because you're squaring it. So it's usually 0 point something. 1 would be a perfect correlation. So you don't have the negative and positive here with the coefficient of correlation, sorry, the coefficient of determination doesn't tell you if it's negative or positive. It just tells you the fraction of the variation in y that's explained by x. But you have something else that you get from the regression, and that is a slope equation. And if you remember from calculus, y equals a plus bx. Sometimes it's written y equals bx plus a, or y equals mx plus b. You can use different letters, but there's always a y on the left side. There's always an x that's multiplied by a letter, another letter, plus another letter. And what this is the slope equation. A is the intercept, B is the slope. And if you know the intercept and the slope, then for any value of x, you can predict y, right? Within a certain amount of error, plus or minus. Handy, right? This is what tells us the answer to those questions of how much does blood alcohol level change for every beer I drink, right? Well, if I say if I drank 2 beers, I put X in here, then I know the slope, multiply that by the slope, 2 times the slope, plus the intercept, which should be 0 in this case, because I should have 0 blood alcohol content if I didn't drink any beer, unless I was drinking another kind of alcohol. Never mind that. Then you would be able to predict my blood alcohol content. Boom. Graphs. Okay. Graphs here are very, very similar. Again, subtle differences. With the correlation, you get a scatter plot with the points only. No line, no regression line. You'll see people do it. Sometimes I forget and I do it too. It happens. But technically, you shouldn't have a regression line on a correlation. If you do, it's a regression. Now, with a regression, you get the scatter plot with the least squares regression line, which is so awesome. So here for this example, we look at on the x-axis change in non-exercise activity in calories. And the y-axis has fat gain in kilograms. This is an example from the book. On the left graph, we have no regression line. This is taken from the correlation chapter. And on the right side, we have the same x and y axis. This is taken from the regression chapter. And the regression line predicts fat gain from change in non-exercise activity. And here you could actually see, look, if you have a person who had 400 calories of non-exercise activity, then their predicted change in fat gain would be about 2, right? 2 kilograms. This is how you then predict. Now, if an actual person might, look, this actual person maybe had 400 calories and their actual gain was closer to 4. But if you take this least squares regression line and you use it to make predictions, and you have a strong correlation, your prediction will usually be pretty good. All right, a little bit more about scatter plots. Now, scatter plots are something you've probably all been using since grade school, but just a reminder how this works. It's used to display quantitative bivariate data. Your x-axis is your horizontal axis. Your y-axis is your vertical axis. And each observation is a point. Each observation is a point on the graph. Did I lose you for a second?
No, all good.
Oh, good. Okay. I heard a blink, blink, and I thought maybe I lost my internet. Starting to rain. So in this case, student 7 is this point here who drank 3 beers and had a blood alcohol content of 7. That's how the scatter plot works. Now, again, with the regression, we get the least squares regression line. Why is it called the least squares regression line? Because it is the line that makes the smallest or the least squared sum of the vertical distances of the data points from the line. And here, let me explain a little bit more. So here's number of beers on the x-axis, blood alcohol content on the y-axis. And here you can see every point, unless it lies right on the line, there's a distance of that point from the line, a vertical distance of that point from the line. These are the y distances. That y distance, that red arrow, is the difference between the observed value and the predicted value. So that distance to line is the difference between your actual y and your y hat, or your predicted y. In this case, it would be negative 0.028 for the point that's below the line. And for the point above the line, it's 0.070, right? So it can be either positive or negative, depending on whether it's above or below the line. Now you square all those differences, right? You square all the differences and you sum them up. That's this least sum of squares, least squares regression line. Is that kind of making sense? Okay, a little bit more about residuals, because residuals were a concept that I found hard, so I'm going to make sure you have a little extra time to understand them. So here's another graph that shows empathy score on the x-axis and brain activity on the y-axis. Here is subject one. The distance or the difference between the actual brain activity for subject one and the predicted brain activity for subject one is the residual for subject one. It's how much of a mistake is that least squares line. It's never going to be perfect. So how much error is there in our least squares regression? How much error is there in our prediction? Add up, square all those points, sum them up, and that's how you get the least squares. And these residuals themselves can be plotted on a scatter plot. So here we have the empathy score again on the x-axis, but on the y-axis, we put something different. Instead of the brain activity, we put the residual itself. We put that distance. And the residuals should always have a mean of 0. So there should always be a straight line here. And what you usually want to look for is whether or not there's a pattern in the differences between these lines and these points. So is there any kind of a pattern? Here it looks like a random cloud, right? It's a random cloud of points. That's what you want. You want a random cloud of points. You don't want to see a pattern. You don't want to see that the residuals increase with increasing empathy score, right? You want it to just be a random, normally distributed cloud. And we use these residual plots a lot to test for equivariances. Remember, that's the fourth assumption, fourth condition we have to make. We need to look for whether or not our regression meets the assumptions. So we make these plots as part of the process of doing the analysis to check our assumptions. Just like before we made histograms and box plots to check our assumptions, here we make residual plots. And we can also make histograms and box plots of the residuals to check our assumptions of equivariances. So for the simple linear regression to be valid, our residual plots should show a random pattern, like in that first slide, right? Here's a random pattern. There's nothing going on here. It's all over the place, like you just threw rice on the table and it's scattered. Now, if you see a non-random pattern, especially like a U shape, if your data is smiling or an inverted U, or if it's frowning at you, if your data is making faces at you, you got a problem. Right? It means that there's something about your data that don't meet the assumptions. Usually that there's a variation is not equal across all levels of X, or that it's not normally distributed. And that might mean that you either need to transform your data or use a different analysis, like a nonlinear model. Okay, interpretation. The interpretation that we use for these two forms of analyses are also somewhat different. They both tell us different things. They're both great because one tells us one thing and another tells us another thing. Correlation, we get the R, the Pearson's correlation coefficient, and it tells us the strength and direction of the relationship, right? -1 would be a super strong negative correlation, +1, super strong positive correlation. The regression tells us something different. The R squared tells us the proportion of variation in Y that can be explained by X. And we get the slope equation that predicts Y from X. And I know I said this before, but I'm putting it here again because this is really important to remember. Interpreting scatter plots. When you want to interpret the scatter plot, Think about these 4 different things when you're thinking about how to describe the overall pattern of the relationship. You want to look at the form, the direction, the strength, and whether or not you see any outliers. If you see a really nice linear relationship with no outliers, super duper. This is the relationship between powerboats registered in thousands and manatee deaths from powerboat collisions. That's a nice linear relationship. Okay, a correlation or linear regression analysis would probably be valid in this case. Form. What do we mean by form? The form of the relationship between 2 quantitative variables describes the overall pattern. Okay, there we go. Again, here you see a strong linear relationship, right? It's a linear positive relationship. Here we see a weak or no relationship. It looks almost like a random scatter, like you maybe see an increasing trend, but then there's this point over there. It's really hard to tell. It's hard to tell if there's any pattern going on here between height and hand length. Or here, where we look at termite activity in fairy circles and grass plants per fairy circle patch, we see a non-linear relationship. Some relationships are linear. It's very common in nature, but it's also very common to have non-linear relationships. Sometimes you can transform the data to make it linear, and sometimes you just do a different kind of analysis. The second thing you look at in the scatter plots when you're thinking about the overall pattern of the relationship and how to interpret it is the direction. Really simple. Is it positive or negative? The positive association is when you see the line going up towards the right. It means high values of your X variable tend to occur with high values of your Y variable. Y increases with increasing X. Positive relationship. A negative association or negative relationship is when it goes down to the right. High values of one variable tend to occur with low values of the other variable. So you get Y decreases with increasing X. This is change in non-exercise activity with fat and grams. The more you exercise, the less weight you gain. That's a negative relationship. Probably a good negative relationship, right? More power boats registered, more manatee deaths, positive relationship. More non-exercise activity, less fat gained, negative relationship. Then there's the strength of the relationship. The strength tells us how much variation or scatter there is in our scatter plot. A strong negative relationship would mean that all the points cluster tightly around the line. Whether or not you see the line here, we didn't draw the line on here, but you can see that if you were to draw a line, all the points would land very close to that line. Now, and this is time since onset of cold versus cold symptom severity score. So this is telling us that there's a strong negative relationship in the time in days since the onset of cold and the cold symptom score, which makes sense. You feel less sick as time goes on, right? Now, here we have a weaker negative relationship. It's still a negative relationship. We still have the same direction, but the strength is different. You see, there's more scatter around any sort of imaginary line that you would draw. The points are further from the line. They're more of a cloud. And this is the relationship between serotonin transporter level and straightforward personality score. There's probably something else that's affecting straightforward personality score. And so there's only so much variation in your Y that can be explained by X because there's a weaker relationship. If you wanted to know exactly how strong, you'd look at the correlation coefficient. And here's an example of correlations with different correlation coefficients. Again, to illustrate the point of the strength and the direction of the relationship as shown by the correlation coefficient, we have here on the top a correlation that equals 0, random scatter of points. How about a correlation that equals -3? That would be a weak negative relationship. How about a correlation that equals +5? That would be a stronger, a moderately strong, you could say, positive relationship. If you had a correlation of -0.7, you could say that your correlation was also fairly strong negative relationship. If your correlation is 0.9, if your R is 0.9, you could say you have a strong positive relationship. And if your correlation is -0.99, you would say you have a very strong negative relationship. This is how you would interpret these graphs. This is what your correlation coefficient gives us. Again, R ranges from 1 to -1 for perfect correlations. And a negative R means a negative relationship, right? These are all negative R's, negative relationships. Positive R's, positive relationships. The other thing you want to look for in your scatter plot, outliers. Outliers. Correlation and regression are both very sensitive to outliers. Moving a single point away from the linear pattern can weaken the correlation, in this case, from 0.91, -0.91 to -0.75. Here we imagine we have time to swim 2,000 yards in minutes and pulse in beats per minute. And for this sample, we have a very strong negative relationship. Our R is -0.91. All the points fall closely along the line. But here, we moved 1 point from here to here. And that changed our correlation coefficient all the way from 0.91 to -0.75. It completely changes the correlation. The points don't fit as well because of that one outlier. I like to imagine this is Michael Phelps, right? I just try to imagine, okay, time to swim 2,000 yards in minutes. Like somebody swam 2,000 yards, the shortest time, or as some Olympic athlete, right? The rest of these points are normal people. And this point is the Olympic athlete, the person who swam 2,000 yards faster than anybody else and didn't even get his heart rate up, 130. He didn't break a sweat, which of course makes sense because he's in the water, but you know what I mean? It was easy. It was easy for this person to swim really faster than everybody else. That's an exceptional person. Sometimes outliers are interesting. Sometimes outliers are what you want to see. Sometimes outliers are mistakes in data entry. Probably most of the time they're mistakes in data entry, but sometimes that's actually the interesting thing you want to know about. Outliers and influence. Okay, important distinction. There are outliers and then there are influential points. They're kind of different. An outlier is any observation that lies outside the overall pattern, right? It has a large residual. For example, this orange point here is an outlier because the residual is really large. It's far away from the predicted value. But because it's in the middle of the data, it's in the middle of, roughly in the middle of your X, it doesn't have a strong influence. The influential individual is an observation that markedly changes the regression if removed. And this is often an isolated point on either extreme of your X range. So this point over here in blue is all the way on the upper end of your X. If you removed this point, it would probably change or shift your regression line. The influential individual has what we call leverage. It can lever that line up or down, mostly because it occurs on the extremes of your X. Another example of outliers and influence. So how do you know if a point has influence? Well, there are tests we can do for leverage. There's a test. We'll go over that later. But one way, very simple way that you can test it is just take it out. Remove that point, rerun the regression and see how much it changes your correlation coefficient. See how much it shifts your line. So here's an example. Here we have this outlier here again in orange and this influential observation in blue. So this solid red line represents all the data together. You see where it falls in the middle of all the data. Now, if you took out the influential observation, you could see that changed the line a lot. It went, one end popped up because this influential individual wasn't pulling it down. Now, if you change the data by removing just the outlier, you can see that both of the solid lines are pretty similar. So how much is a lot to move it? How much is pretty similar? I know it's a little bit vague. It'd be nice to have something more black and white to tell us, yes, this is an outlier. Yes, this is an influential observation. Yes, there are tests for that, and we will do them. We will do them so that we'll know. But just to get the general idea, outliers may or may not have an influence on your regression. If they're an outlier and they don't influence your regression, no problem. But if they are highly influential, it may mean that there's a problem with your analysis or that your predictions are not going to be as accurate because of that one individual. And you may need to adapt your analysis or even your experiment. How to write the conclusions. How to write the conclusions. You will need this, of course, to do your reports and your homeworks. So for correlation, again, remember that R tells us strength and direction of the relationship. So if we had this graph here, time since onset of cold in days, and cold symptom severity score. Now, again, if we're only doing a correlation, we won't have this line, but we would have an R value. We would have the correlation coefficient. And if our correlation coefficient was negative 0.97, we could say there is a strong negative relationship between days since onset of cold and cold symptom severity score, right? We know that our relationship is both strong and negative. And actually, we should put in here our R. R equals negative 0.97. Now, the regression tells us something slightly different. Remember, R squared tells us the proportion of variation in Y that can be explained by X. So we can say cold symptom severity scores decrease with the number of days since onset of cold, R squared 0.95, P negative 0.001. Oh, you can get a P value for correlation, but most of the time you're just looking at the strength and direction. Or you could say time since onset of cold in days explains 95% of variation in cold symptom severity scores. And again, you put your R squared and your P value. That's better, right? More than just saying that it decreases. Now you're saying how much variation is explained. So time explains like 95%. So should you take medicine? Well, if 95% of my symptoms for cold are going to decrease if I just sit and wait a few days, then that's all I need to do, right? You can also then say cold symptom severity scores decrease by whatever your slope is for every day since the onset of cold, R squared 0.95 less than 0.1. I don't have the slope for this particular regression right now, so I just put in that you just put in the slope there. You could also combine this statement to put all of that in together, like cold symptom severity scores decreases by X slope for every day since onset of cold, which explains 95% of variation in cold, right? Put it all together, package it up neatly. Now you know a lot more about how days since you started having a cold affects your cold symptom severity score, right? Tons of information. Let's practice doing this interpretation a little bit. So if we had this graph here, we had serotonin transporter level in units of dorsal racemine nucleus as regressed onto straightforward personality score. How can we interpret this graph using results from the correlation? This is our correlation coefficient here is negative 0.538. Right. Well, again, we could talk about the strength and the direction of the relationship. We could say, well, serotonin transporter. Oh, wait, let's start with talking about our Y. Straightforward personality score decreases moderately strongly with serotonin transporter level, or serotonin transporter level and straightforward personality score have a moderate negative relationship. Because I guess it doesn't matter if you're X or Y, right? Think about it. I don't know very much about this, but who knows which really should go on X or Y? Although I guess for the regression, you have to say that you believe that serotonin transporter level is what affects the personality score and not the other way around. If you're doing the regression, that's your assumption of putting that value, that variable on the X and the other variable on the Y. And if you're going to write your interpretation, your conclusions for the regression, and you get an R square of 0.290. Now, if you just had the R square, you wouldn't know the direction, right? But if you look at the graph, you can see, oh, that's a negative relationship. And you can see the amount of scatter. So even without the correlation coefficient, you get an idea that it's a moderate negative relationship. Although having that correlation coefficient sure is handy. Also, the slope would be negative. So if you have the slope equation, you would know that it's a negative relationship. And you could say serotonin transporter level explains about 29% of the variation in straightforward personality score. These two variables have a negative relationship, or straightforward personality score decreases with serotonin transporter level, which explains 29% of the variation in personality score, right? Dangers. I told you there would be danger ahead. What kind of danger? What kind of danger could there possibly be? Well, one of the dangers for both correlation and regression is that you might have nonlinear relationships. You need to look at the scatter plots and determine whether or not your relationship is linear. Does it make sense to do a correlation or a regression analysis, a linear regression analysis? You also have to look out for lurking variables, which are factors that could affect your Y other than X that you didn't include in your analysis. Now, remember, with correlation, you can only include two variables. So if there's something else affecting Y besides the X, you don't know. With regression, you could include multiple factors. So you can take those lurking variables into account. Another danger is that correlation does not imply causation. And I sent you a video on that, but we'll talk about it more here too. And with regression, you have a fourth danger, and that is extrapolation. And that's not a danger you have with correlation. All right, let's look at these four different data sets and think about, is linear regression appropriate for these data sets? Set A shows a moderate association. So you would think, okay, regression is probably appropriate. It looks like a roughly linear relationship. Set B is clearly nonlinear. Regression is probably not appropriate. It looks like a curving, it's a curving limit. It's maybe exponential something relationship. Set C has an extreme outlier, and since that extreme outlier is on one extreme end of the x-axis, it's probably also an influential observation. This would mean that any predictions you make using that regression equation probably will be off. That is, if you were going to say, predict whatever your predictions of 11 would be, are not really what 11 is. And that again, that might be a data entry error, or it might just be a fluke. Set D has only 2 values for X. This has only 2 values for X. What happened here? Well, what probably happened here is that your X variable is not a continuous numeric variable. Probably what you have here is actually some kind of a categorical variable disguised as a numeric variable. Possibly. Or it could just be that you took a lot of measurements right around 6, 8, 9, 8 or 9. Yeah, 8. You took a lot of measurements at an X value of 8. And you only took one measurement at an X value of, was it 18 or 19? Maybe that's all you could. But in that case, still, regression is not going to be appropriate, unfortunately. Do you see this sometimes in ecological studies, especially where you just don't have that great of a range? Yeah, it happens all the time. Watch out for it. Danger. Now, when you have a non-linear relationship, sometimes you can transform one or both variables to make that into a linear relationship. One of the most common transformations is the logarithm transformation. And it's often used when your data are highly right skewed, which happens a lot. Our data has been right skewed a lot, right? Now, remember when you do this, that when you want to make predictions using your regression equation and you've transformed the variables, you have to back transform to get your predicted y in the same original units. Otherwise, it won't really make much sense. Okay, so for example, if we look down here at the graphs of body weight in kilograms and brain weight in grams, very common relationship. And here you have each individual point is a different species. You have hippos and humans and dolphins, and elephants are just so much bigger than everything else that was measured, that you have this really extreme influential point that can tend to throw off your predictions. One thing you can do to sort of smear those points out so they go evenly along the axes is to transform your variables. And in this case, you can see on the X and Y axis, we have the logarithm of body weight and logarithm of brain weight. So both X and Y axes were transformed, were log transformed, which just means you essentially sort of multiply by a constant. You multiply each value by a constant. It's really easy to do. And now you can also see that it changes the axes values. So here we have body weight going from 0 to 2,800. Here we have body weight going from -1 to 3. It changes the values of your axes in a way that makes them pretty hard to interpret, actually. It's easy to interpret, okay, these values are around 0. This is about 400. This is, okay, I can kind of picture what 2,800 kilograms is. Can I picture what the log transformed 3 kilograms? No. My brain's not that fast to do the log transformation. So often when you actually display your data, you'll want to display the original values. But here you can see that it makes a nice linear relationship between these variables as long as you log transform them. But then when you want to back transform, you want to get your predicted brain weight, let's say you want to get the brain weight when the body weight is equal to 100 kilograms, right? You want to say, okay, if my body weight is down here, what is my predicted brain weight? What should be right on this line? Well, then you'd say, okay, log brain weight is equal to 1.01. That's our intercept, plus the slope, 0.72 times log body weight, right? So again, log brain weight is equal to our intercept of 1.01 plus the slope of 0.72 times 2, which is our log body weight, which is equal to 2.45, which is totally meaningless to the human brain until we back transform it so we can get back to regular grams units. And to do that, we simply take the inverse log, which is, since we log transformed it using the log 10 transformation. Remember, there's two kinds of log transformations. There's the natural log and log 10. They must have used log 10 here because it's 10 to the power of 2.45, right? Here's our 2.45. We take 10 to the power of 2.45, and that's equal up to 282 grams. Aha, now we're back in normal units that a human brain can understand. Humans here with our puny brains. Actually, our brains are kind of big compared to other mammals in our size class. Hippos, probably kind of dumb. Sorry, hippos. On the log scale, you fit right in there. Lurking variables. Lurking variables. Okay, here's an example of a lurking variable. I don't think I really explained very well what a lurking variable was, though. Well, a lurking variable is a variable that affects your y that you didn't account for. Here's an example. The relationship between muscle sympathetic nerve activity and a measure of arterial stiffness in young adults was measured. And on the upper left-hand corner, you see if you put sympathetic nerve activity in bursts per 100 heartbeats on the x-axis, and then on the y-axis, you put augmented aortic blood pressure in millimeters per grams of mercury, millimeters per mercury. You would look at this scatter plot, these green dots, and you would think there's no relationship. There's nothing going on. Your R squared is 0.02. If you put a line on there, your slope would probably be about flat. So there's not a relationship between these two variables. X explains less than 3% of Y. Not important. But here, both males and females were included in the graph, and apparently males and females have a different relationship for these two variables. So if you take males and females and you graph them separately, you put males over here, and of course they put that in blue dots, and you put the sympathetic nerve activity and augmented aortic blood pressure, you can see now that there's a moderate positive relationship between these two variables, and that sympathetic nerve activity actually explains about 29% of the variation in augmented aortic blood pressure. Whereas for females, the relationship is opposite. It's a moderate negative relationship that explains about 33%, or about both ways. It explains roughly a third of the variation. But for males, the relationship was positive. For females, the relationship was negative. So when you put them together on a graph, it looks like nothing's happening. So in this case, gender would be the lurking variable. Correlation does not imply causation. This is something that's really important to understand. The association, however strong, does not imply causation. Even with regression, where our goal is to predict, we don't necessarily know that just because we can calculate a predicted Y for every level of X, it doesn't really mean that X caused Y. We just know that they change in this pattern. The observation could have another cause, a completely external factor. So this a lurking variable is a variable that is not among the explanatory or response variables in the study, and yet may influence the relationship between the variables studied. There we go, there's the explanation. So we say that two variables are confounded when their effects on a response variable cannot be distinguished from each other, right? For example, when researchers measured the association between chocolate consumption and the number of Nobel laureates per 10 million people in the population, with each country as an observation, they found that chocolate consumption had a strong positive relationship with the number of Nobel laureates, or the proportion of Nobel laureates in the population. And it explained about almost 63% of the variation. Yeah, but what would the mechanism be for that? I mean, does eating chocolate really make you so much smarter? Because I'm willing to give it a try. I'll eat as much chocolate as necessary. Or could there be something else going on? What other factors might be related to these two variables? In other words, what are the lurking variables? What besides chocolate consumption might increase the proportion of Nobel laureates in the population? Or you might think, what factor might increase both chocolate consumption and number of Nobel laureates? Like money, right? So countries that have more money might, have people that both eat more chocolate and be more likely to be doing the kind of high level work that results in a Nobel laureate. So that would be those factors are confounded. The lurking variable is probably income, or it could be size of the population. Well, this is chocolate consumption per capita in Nobel laureate. So they're both proportions. So maybe population size wouldn't be it. But yeah. Or, yeah, but still population size. They're just like a lot more people in some countries. All right. Please do watch this video. It's short, it's fun, 12 minutes. You'll enjoy it. It's going to give you some really fun examples of how correlation can be mixed up with causation. And on to the final danger here, which is extrapolation. Oh, and I sent you a link for this video yesterday. It's on La Lima. I sent an announcement. Click on it, watch it. Extrapolation. Okay. So we know that the equation of the least squares regression line predicts y for any value of x, but only within the range studied. Prediction outside the range is called extrapolation, and extrapolation can be really, really risky. And here we have the example of beers and blood alcohol content again. So what would we expect for the blood alcohol content after drinking 6.5 beers, right? 6.5 beers is right here. So if you take predicted y equals bx plus a, then that would be a slope, right? Here's our slope of the equation on the graph, 0.0144. So we take 0.0144 times x, in this case, 6.5, plus the intercept. Here's our intercept, 0.0008, right? Now, if you multiply our slope times our x, you get 0.936 plus the intercept, and then you get 0.094. So the blood alcohol content would be 0.9. Now, is that far outside of our range? No, that's not far outside our range. But what if you tried to, whoops, oh, I thought this had another section here. It should have another section here where it says, what if you tried to extrapolate for someone drinking 20 beers? Well outside the range. Or perhaps a better example of this would be, let's say you looked at the relationship between age and height. So you started off by measuring children between the ages of 5 and 10. And you have a regression to predict how much height increases for every year for children between the ages of 5 and 10. Now, what if you use that same regression equation to predict the height of a person at the age of 20? Well, they'd probably be 10 feet tall. It wouldn't make any sense because that's not a linear relationship that goes on past a certain range of values of X, right? Also, I think for most people, 10 beers, they'd be on the floor already anyway. I would. I'm a lightweight. Okay, here I'm just going to throw at you the non-parametric version of the correlation, which is the Spearman's rank correlation. So if you have outliers, you can use the Spearman's rank correlation, and it uses Spearman's rho instead of R is your result, which is a little confusing because we talked about rho being the population correlation coefficient, right? But here we're talking about Spearman's rho. Spearman's is also a great way of doing the correlation. It just uses a different underlying math, but it still gives you an idea of the strength and direction of the correlation. This table here sums up everything I just told you, more or less. This is your study guide, your cheat sheet to correlation versus regression. And yes, I am sending you this lecture. I'll upload it right after I get done with this class. Both correlation and regression use two continuous variables, but with correlation, you don't want to suggest causation. Just look at the relationship between the two variables. X and Y axes can be flipped. With regression, you actually want to predict how the response variable changes with changes in an explanatory variable, right? You have one thing that you think affects the other. Plots. With correlation, scatter plot only, points, no line. With regression, you make a scatter plot with the points and the least squares regression line. The null hypothesis for the correlation is that there's no relationship between X and Y, which is very similar to regression. You say there's no relationship, but specifically the slope is equal to 0 or the beta is equal to 0. The test statistic or the statistic of interest essentially for the correlation, it's not the test statistic. This is not including the test. This is just the statistic that you get that tells you about the relationship is R, which is telling you the strength and direction of the relationship. R squared for regression tells you the proportion of variance in Y that's explained by X. Can you get a p-value for these both? Yes, you can. I'll get into that more after the midterm. We'll talk more about getting p-values for regression in particular, because it varies depending on whether you're doing simple linear or multiple linear. And do you get a slope equation? So for correlation, you do not get a slope equation. For regression, yes, you do get a slope equation. Here's your handy dandy cheat sheet table. Wrapping it up at the end. There you go. Questions?